Hello everyone. So I guess the hackathon is officially over. Should be just start, in my opinion. So hello everyone, and thank you those that participated. So basically, we had a few submissions. I think a total of 6 people took part in the end, and I'm going to forward basically the standings, and I'm going to show the standings of the top 3. And basically, we have share Andre with a score, impressive score of 81%. I'm going to put this in the chat. Then there's Philip with 78% and myself with 76%. So what I was going to do now is I'm going to ask Andre to basically guide us through his test. If I'm not mistaken, Andre, you did a neural network for this, correct?
Sorry, I missed that. What did you ask?
Yeah, so for your score to get an 81%, you were able, so to do that, you did you built a neural network for this, correct?
Right.
Yeah,
That's correct.
Yeah, so basically it would be nice for the people here if you could just go quickly through your notebook and like what your like methodology was and how you achieved your 81%.
Right. So so I think I'll just open the code here. Hang on. Right. Hang on. I'm sorry, what exactly can you see right now?
We're not seeing anything at the moment. You should be able to share.
I'm sorry, I hope this system soon. Okay, now?
Yeah, everything is fine.
Okay, is the code well readable?
Yep.
All right. So I don't really have a lot of comments here, but I don't think this is very complicated. The thing is, I actually defined 3 networks because I wanted to make use of both the data from the signals themselves, and all this other environmental data like geographical coordinates and stuff.
Okay.
So what I did was define one network which just handled the signals, one which just handled the other parameters, and then one which combined all of this together. So the first one, the one with just the signals, is a convolutional neural network, is the one here. It's this one with 4 layers. And in the end, there are 24 channels. And the second one for the parameters is this one over here, which is a dense one with 4 layers. And for both of these, I used the Lee-Ke-Ri-Lu activation function. And then the one which combines the outputs of both of these is this one over here, which is again dense, but unlike the previous ones, uses the sigmoid activation function, and it has 3 dense linear layers, and there are also dropout layers. And at the end, there is a softmax function to normalize the outputs so that it gives probabilities for the different classes. And for the actual classification, I simply used I simply took the class with the highest probability. All right, and I go back to the previous code, which was the actual training script. This here that you're looking at right now is just like a data representation, which converts the data set as given as a pandas data frame into a torch tensor. So this is all very standard, but the method itself, hang on, is only actually this part here. Hang on, this part here. So I used the binary cross entropy loss for optimization, and the optimizer was Adam with an initial learning rate of 0.0001, so 10 to the minus 4, and a gradual decrease of the learning rate throughout the optimization, with a batch size of 32, and this here highlighted right now is just the training loop, which is quite standard. It's just some places are a bit longer because they include the actual passing through the inputs through the different networks. So it looks a bit longer, but there's I don't think there's anything unusual to it. So so this right here, from where the cursor is right now, is just passing the signals through the network, and here the other parameters through the network joining this, and this right here is already producing the final output. So just like these 4 lines are what would usually be a single line. So that's what's making this look a bit longer. But the training method itself is very, very standard. The main trick was using the 3 different networks and combining the outputs of these. Right. This final block of code right here is just like a final accuracy check. So I think that basically sums it up. Did that seem clear enough?
Quick question. So when you were using not the metadata of the signal, but the actual the signal themselves, the E, the N, and the Z, how did you combine them into your new network?
Hang on, I'm not sure I understood right now.
So you said you had 3 networks, yes? So one network used the meta information of the signal, so what type of maximum frequency, etc. You had the other network which used the actual signal themselves, correct? The actual
right.
E and in the Z trace. Yes. Right. So
yes,
in that one, what type of network did you use there in that instance? So could you was that a convolutional one as well?
No. So only the one that handles the signals themselves is convolutional. The other 2 are both only with dense layers.
Yeah. Okay. So you had 3 traces, yes? So you had a trace of E, which was 6,000 samples, and then you had another one which was N, which was another 6,000, and another one which was Z, which was 6,000. Did you like stack them on top of each other? How did you go? Or just did you run 1D convolutions on them? How
yes,
did you go?
Yes, I stacked these. The input for the signal network was basically like a 1-dimensional image with 3 channels, E, N, Z.
Yeah, okay. So you stack them on top of each other, okay. And then you run convolutions across, exactly. Okay. Oh, interesting. How did you choose this architecture, or did you just go for this?
Well, I I wasn't exactly sure how to start with the task, but I have a little bit of experience with neural networks, so I thought that might be a good start. And I remember the paper where I saw.
Can you just mute? Sonia, can you please mute, please?
Yeah.
Okay.
Okay. So I remember a paper in Gravitational Waves where I saw that that the team took like a convolutional neural network with without any dense layers at the end.
Yeah.
But then created several networks with only dense layers. And when they passed the gravitational wave signal through the convolutional network, then they would take the output of that and pass it through the different networks with just dense layers, and one would output the component masses of the binary, one would output the quasi-normal mode frequency, and so on. So this is this was kind of
Okay.
yeah. So this is kind of what inspired me. I just had to like reverse it, and instead of using different networks to do different outputs, to use different networks to do different inputs.
Yeah. So it's interesting because what you did is basically what researchers have done when they've created what is known as a ConvNet quake. I've actually shared the paper for you. And this is exactly what they did. They just stacked the three traces and they just ran convolutions on top of it. So quite interesting that you saw an application of this in a completely different field and you've managed to bring it across. So quite interesting. And it actually, to be honest, I like your idea where you still used, let's say, the meta parameters of the signal themselves, which would not necessarily be visible in a temporal sense. Because what you did, since you're running convolutions on just those traces, you are missing out on, let's say, some frequency style information because you're only using temporal. But yeah, I like your approach. Well done. Okay, so
Thanks.
I guess I can now ask Philip, who got rank 2, to potentially share his notebooks to see exactly what his approach. And if I understood correctly, you went for the machine learning random forests approach. Is that correct?
Yeah, well, I tried a couple of various things, a couple of different algorithms actually, but random forest turned out to be the most effective. So basically my idea, well, first of all, can you see my screen?
Yep.
Okay, perfect. So my main idea was to include batch of additional meta parameters, new features based on actually the signal. So let me show you what I mean. So I tried to analyze also like those let's say raw signals, those kind of components En and Z, but it turned out that it's not working too well. At least with some neural networks I tried, maybe not too complex models, but I also didn't put too much effort into this, so I decided to stay with metadata. So I thought that basically it would be nice to add some information to metadata about the Fourier spectrum. So what I did, as you can see here in this, basically this module, this function getMeta, I computed PSD, and based on this PSD, I generated a couple of let's say additional informations that are usually used in signal processing. So you have some information about the mean frequency of the PSD, some maximum frequency, some signal to noise ratio. That's like in the peak, the duration of the signal, and let's say kind of when it starts. Because like once you have like this segment of time, like the signal might start at various points. So I thought that, yeah, well, might be good to also include this information. And I repeated this step for all three components, E, N, and Z. And yeah, actually, I got 15 new features. And it turned out that just with this, I could, and obviously like adding it to the previous features, I could easily reach 78%. So then I tried to tweak a little bit like the random forest classifier, changing those meta parameters. And I think that one can get even better results with just, this new metadata, but I just, let's say, didn't have enough time to invest this issue, but definitely I think just following the analysis of PSD, it's really worthy. And basically it works. Maybe I can show you how PSD looks like in our case. Yeah, so it's something like this. And for various components, it differs. For noise, it's obviously, again, much different. So yeah, basically that was my idea, to generate some new features and study them using some relatively simple machine learning models. So that's all. Questions?
Philip?
Yeah.
Can you hear me? So
Yeah,
basically, to plot the PSD, I missed an information. You used all three channels or three separate PSDs?
3 separate PSDs.
Okay, cool.
And for each of the PSD, I generated this bunch of meta parameters. Though I also tried to, let's say, combine signals in various ways and try to make PSD on top of them and then generate new features. But it didn't work as good as analyzing components separately.
Okay, cool. Thank you.
All right. So that's all on my side.
Okay, thank you, Philip. So I guess I came in third, and I can show you quickly what I did. I followed very similar approach to Philip, in the sense that so everyone is seeing my screen. So let me just go quickly to a new one. So I followed Philip's idea of using a so what I did was, I can explain. So let me so I was running some tests. So I have 2 notebooks. So the first notebook was just running a couple of modeling, so logistic regression and decision trees and random forests. And when I was looking at the learning curves, you can see that if I add more data, I'm actually getting better scores on a cross-validation. So I needed to augment my data. So what I did was, I just took my E, N, and the Z traces. I then considered only the noise. So you can see I've just picked only the noise. And I took the mean noise level for each E, N, and Z. And then I randomly added noise to my traces, and I augmented my waveform from originally 15,000 to 61,000 traces. So added noise to my traces and generated new data. I also added a couple of additional traces by using smoothing. So I took my original E and Z and I smoothed it on 250 samples and 1,000 samples. The idea here was that the same thing that Greg mentioned with the short time versus long time windowing. If I had to use a rolling window, I can remove some of the resolution in my trace, but then I can do calculations, time-based calculations on top of those. So that's the idea here. And basically for my original 6, which were my label target trace ID E and Z, I ended up with 12 because I added 6 new traces of sorts. And I then just calculated some interesting features. So what I did here was I did some literature review, and there's actually seismic features for AI. So if you had to go to this guy here, Musavi, on his GitHub, he actually has seismic features for machine learning. And this is a paper which basically they go to a bunch of metrics applied to classification of traces. And you can see, for example, the maximum amplitude, the spectral centroid. And they also did a, I'm trying to find the table, the result section here. This one. So this is the feature importance of each seismic feature that they added. So the spectral centroid was quite an important one. The degree of vectorality as well. So basically what I did was I calculated some of these features as much as I could. And I just added, for example, the spectral centroid, degree of vectorality, RMS, etc., etc. And I ended up with 40,000 traces as my train with 96 features, 10,000 as my test, and 12,000 as my validation. So I wanted to see how good or bad without actually exposing the validation to my testing and training. These are my columns, so you can see all of them here. And as a first approach, I tried different modeling techniques. So logistic regression. So you can see my accuracy is not doing pretty well. Noise is excellent, but the others is pretty bad. For decision trees is looking pretty good. So you can see my arrow curves doing pretty well as well. My positions on the high 90s, so pretty good as well. But for my cross-validation score, if I had to add more data, I could potentially get a better score as well. Then the forests, even better. So you can see like my precision, I have some which are ones, so pretty good, darn good. Everything looks pretty well as well. Gradient boosting, so not doing as good. Can add a bit more data as well. ML, so this is a neural network with a couple of layers. So just trying it out. I mean, can do a bit better, not the best result. Gaussian, pretty bad, only bad, so did not pursue it. And then the other thing I did was I've presented all my results and I picked the top 3 performers, which was my 95, 85, and 95 here, basically, yeah. And I stacked them into a mega estimator using a voting classifier. So this is similar to what Andre did of sorts, where he used a sigmoid to combine multiple estimators. So I had 3 estimators in my case. So I combined them using a sub-voting, which looks at probabilities, and I got my final result with an accuracy of 98%. And this is what gave me the result. So this just creates the submission. Okay. Does anyone have any questions?
Yes, I would like to ask you, well, when I was trying to add some, meta features, then generally the differences between the, let's say, final results on on submission and the test set weren't that big different. And it seems that in your case, it was like more than 20% of accuracy in general of difference. And do you have some idea why it was like as big as this?
Yeah, because I ended up augmenting my data. So I augmented my data a lot, that's why. So basically, if I go back to my code, I can show you my code. If I go back to, so this is how I'm augmenting my data. Are you seeing this part? So first I calculate the average noise on the E, the N, and the Z. Then basically I just return a random sign. If it's a plus, positive or negative, basically multiplied by 1 minus 1. So basically, should I add or should I subtract this noise? Just to literally add the noise. And this is how I'm tweaking my noise. So what I'm doing is I'm taking my trace, calculating the noise level. So we're getting it from here. Apply a number randomly between 0 and 0.1, so up to 10%. And then whether should I add it or plussing it? I'm just adding all of this. So you can see from 15, I went up to 61,000. So I added a lot of noise. So I guess that is why we're seeing this big of a difference. So what is considered my test? So because what I'm doing then is, what is my train test? What is my, you can see I'm generating my own train test split here. I'm not using the one originally like given in the problem. So that is why there's big of a jump. The data I have in my test is completely different.
Yeah, well, I'm just surprised because when I was like in the past playing with some augmentation, and well, generally the results on this augmented data were better, but the difference weren't as big as here. So I'm just like, surprised, like just around like 25% of difference. So it's pretty huge.
Yeah, I mean, I think to be honest, I might be suffering from some overfitting. So why would I say this? You can see that the number of estimators, I think this one is, it's always going for the 100 one. And I also have another notebook which adds even more data, and it's always going for the largest one. So I think I'm actually suffering from a bit of overfitting in here. That's why I'm I'm seeing this problem.
I see.
Yeah, so I can show you if you want. Give me 2 seconds. It's in here actually. Copy.
Sorry, Chris, so you added the random noise just to the signal traces or also to the noise traces?
To everything, respective.
Okay, yeah, that seems good.
So I can show you this. So I was running some tests as this was, but basically it was taking a bit too long. So I had some results here. I had to comment them out. But basically when I was, for example, running this, so this one, with a max there, with 500 estimators in my random forests, the best estimator was 500 estimators.
Yeah.
So yeah, I'm like, there was a bit of overfitting here, that's for sure.
No. Well, I also tried like up to 800 actually.
Oh, okay. But I think, to be honest, I could have, with 500 estimators, I should have like reduced this to like that. Would that be a bit better?
Yeah.
So not have like one single trace on the far end or something like that. So my little leaf. So
Yeah, I see
anyways. Okay, but yeah. So I guess thank you everyone for sharing and trying this out. I will be pushing the top 3 notebooks onto the GitHub, and as well as the data I've created a data set on Kaggle, so you can just download the 3 data sets more easily.
Let me just slightly modify mine to add some comments, because now it's like pretty
Okay, no worries. Yeah. So
Agree.
I've added a Kaggle dataset with the test data, train data, submission data, and as well the submission to labels. So whoever wants to play around, even try out some of these notebooks, feel free to do so. Okay. So I guess thanks everyone for participating. By the way, I have the gifts for the winning team, and it is going to be a bag from EGO and a notebook from EGO. Unfortunately, this is what the sponsors gave us. So this is what you guys shall be receiving. I guess we'll have to do this when we meet again in the next training school. And yeah, wish you best of luck. Hope everyone arrived home safely. Okay.
Thank you,
Perfect.
Chris.
Okay.
Yes,
Ciao,
thanks,
guys.
Chris.
See you. Ciao, guys, girls. See you.
See you. Yeah.
Ciao.
Thanks. Bye.